Hello to everyone and welcome to Urbano Hydra Essential Training Day 2. My name is Rino and today we will continue where we left off yesterday. We will talk about setting network elements and water demands, scenario analysis, hydraulic calculation, pipe sizing and pipe diameter optimization, exporting to and importing from EPANET EMP file, and so on. The session will last approximately 2 hours, and after that we will have Q&A and I will answer all of your questions. So let's start with the training. Here we are in Urbano, and as you can see, I don't have any drawing open yet. And the best way to open existing Urbano project is that you first run Urbano. So don't just double click on DWG, because first of all, Urbano has to load with all the functions and then go to File, Open, and standardly open your file that you want to open, or the way that I like to do it, so just take the DWG file and drag and drop it to command line. So that's the way. Of course, even if you okay, here I don't have the raster that I had yesterday, so I will just repeat this procedure. So here I have the training from the day 1, and I will take this TIFF files also and copy it just to day 2. So we have the same example as yesterday, and we are continuing from there. So it's not a problem if you just double click on the DWG file. Everything should load correctly, but the suggested way, the recommended way would be to first open AutoCAD or Civil 3D with Urbano loaded and then open the file. So here is where we left off yesterday. We have our system that we designed yesterday. We have our profiles and we have our cross sections. So today, first time we will see the Hydra panel. Like I said, here on the left, we have our module selection. And today we will talk about the Hydra panel, where we have all the functions related to hydraulic calculation. So first function with which we will start today is the function for setting air release and washout valves. So let's take a look into this function. So if we open it, you will see that we can define here air release valves and also washout valves or mud release valves. And also you can see that we have 2 ways how you can set this equipment. First way is by automatic setting, and the second way is by single or interactive definition. Let's check first the single, which means interactive selection. And now you can see this part of the dialog is grayed out and we have the interactive setting. And now you can select your nodes in plan or in profile. So you can set it in plan, but always it's better to set it in profile, because here you can see where those equipment should go. For example, let's go to this node here and let's define this to be, because this is the slope is changing from positive to negative, so we have an inflection point, and here I will place a washout valve. So just select it and click on apply, and you will see that this custom block or this custom graphics will appear here, suggesting that here we have a washout valve. Let's also find one good point, for example this one here, to place one air release valve. So let's select air release valve from the list and let's click apply, and you can see again this custom block or custom graphics automatically appears here. If you want to delete it, you see there is no delete button, because you're basically not deleting, you are changing the node type. So we can change it back to plain node and just click apply, and now here we see that we have the plain node and no graphics. The other way how you can reset everything at once, you can switch to automatic function, And now we can select all the nodes, so the whole active system, and we can define here set type to node, which says replaces all air release and washout valves with the ordinary nodes. So we will set everything to node. And also let's now check this automatic function. Here you can see that you can automatically set air release and washout valves. And here you can see that it can be applied to all types of nodes or just to ordinary nodes. Let's see what does this mean. First of all, I will select all types of nodes and I will click apply. Okay, let's now check the result. Here you can see, here we have a air release valve. Here we have mud release valve or washout valve. Here we have the washout valve. So the software is automatically checking for highest and the lowest points in our network. And on the highest points, it automatically places air release valves. And on the lowest point, it automatically places these washout valves or mud release valves. So basically, it searches for the inflection points in the network where the slope is changing from negative to positive or from positive to negative. Also, I will show you this really nice function, the search function, where you can select any node in plan or in profile. Select, for example, this node here, and we will automatically zoom to plan, and we can see that here the graphics, this custom block, automatically also changed and updated with this symbol. Of course, this can also be customized and changed, that symbolizes air release and washout valves. And also we can zoom back to profile as well. Okay, and also let's check now the first node of the system, this node here, and you can see that the software also placed here we can see the air release valve. So let's now set a water tank, and we would like to set a water tank to this node here. Okay, to set water tank, we have to go to the second command on the Hydra panel, which is called hydraulic node equipment. So if we run this command, you will see that here we have all the EPANET available network elements. So reservoirs, tanks, emitters, all the 6 available EPANET valves. So pressure reducing, pressure sustaining, pressure breaker, flow control, throttle control, and general purpose valve, and also a pump. As you can see, the valves and the pumps in Urbano are basically nodes, junctions, and not like in EPANET links, but everything is completely connected with EPANET. You will see that later. And also, let's here select this water tank, but first of all, we have to select where. So again, you have this icon for selection. Let's select this node here. And now from the list, let's select water tank. And here you can see that you can set up all the parameters for the tank available in EPANET. So we will set everything as default. So initial water level will be 3 meters, minimum 0, maximum water level 6, and tank diameter will be 15 meters. Let's click apply. And notice now that in the same node, we have both water tank and also air release valve. Also, if we check our data tables, let's expand it a little bit. Let's switch here to node hydraulics, and let's select this node. Here you can see that hydraulic equipment is set to tank. But if we switch to node geometry, you can see here that the node type is air release valve. Okay, let's now go back to our function for setting air release and washout valves. Let's select the entire network and let's set everything to node. So let's delete all the air release and washout valves. Okay, and let's now select the whole system. And now we will switch here from all types of nodes to only ordinary nodes. And let's click apply. And now you can see that the software automatically placed air release and mud release valves, but not in the nodes that are not plain nodes, that are, for example, pumps, water tanks, reservoir valves, and stuff like that. So we still have the air release and mud release valves, just that those hydraulic equipment nodes are skipped. Okay, that's it. Let's now also place this air release and mud release valves to be inside of a manhole, because yesterday I showed you how you can set the manholes from the manhole catalog. So let's now repeat this procedure. I will go to function for setting the manholes from the catalog. I will use the same manhole as yesterday. You can see how the software remembers the last used manhole and all the last used setting. And now, of course, we could go and select just the nodes that where we would like to place these manholes. Or I will use the another way. I will go to select all the whole active system, but I will use node filtering, and I will filter it by node type. And here I will say all the air release valves. Okay, and I will click save. And you will see that here we have now a manhole, and this air release valve is placed inside of a manhole. And here you can see that here the software didn't set the manholes because we used the filtering. Also, let's select now a filter for washout valves. Let's click save, and here the manhole will appear. Okay, so now we set up the water tank and also air release and this mud release valves. Now I would like to save this drawing. Let's save it, and I will save it as working 2, like working from day 2. Let's click save. Okay, and now I would like to open another drawing where I would like to show you some other features about this air release and washout valves in connection with automatic positioning of pipe invert or pipe elevation. So let's take this drawing, let's open it. Okay, here we have one already designed water distribution network. You can see how the network looks in plan. We have all the regular nodes, and you can see this style is applied with realistic pipe dimensions. And we can check this system in profile, but you can see we cannot see the pipes in the profile because we have no invert elevation defined. So if we check our data table for section geometry, you can see the pipes are set from the pipe catalog, but invert elevations are empty. Okay, let's now go to function for setting the invert elevation. So let's go to input data. Let's go to invert elevation. I will use the function for constant depth below terrain. So constant depth below terrain, referent pipe point. So like I said yesterday, I will use axis, but you can use, for example, top outer if you want. So I will set the axis, meaning the center line of the pipe will be 1.5 meters below the terrain. Let's select the entire network and let's click save. And now you will see that the pipes will appear on these positions. And also here you can see that, like I told you yesterday, any data from Urbano can also be added to the profile table. And here you can see the node type, and we have everywhere the plain node. Also, if we open our data tables and switch to node geometry, you can see that the node type is everywhere plain node. Okay, let's now go to our function for setting the air release and washout valves. Let's select the whole system and let's use automatic option and click apply. And now you see how everything is completely dynamic. And now you see how the software inserted a lot of these air release and washout valves with these graphics. Because we placed the pipe to be on a constant depth below terrain, we have a lot of these inflection points. So if we check it in the data table, we will see that in total, we have 17 air release valves. And if we sort it in reverse, we can see that we have in total 16 washout valves. So how we can automatically reduce this number of unnecessary air release and washout valves. So we have on a main panel, so if you click on your home panel, in the workspace, you will find automatic invert calculation function. You can open it. You can create new configurations as well, but I will open this one, which is a default. Let's just double click on it. And here you can basically position the pipe so it follows these rules that can be set up here. So minimum depth below terrain will be 1. And this is the minimum depth of the pipe below the terrain. So this will be the layer above the top outer point of the pipe. So 1 meter above the pipe, maximum depth below terrain, let's leave it to 2 meters. And also you can define minimum slope. And here minimum slope doesn't mean a minimum positive slope. This is the minimum, how should I say it? Minimum positive or negative, so absolute value of the slope, because we don't want our pipes to be horizontal. So we will set some minimum slope to be, let's say, 1 per mile. And additionally, if the software cannot satisfy these rules, the software can additionally convert additional points, so the points where the pipes is crossing the triangles of DTM, to new nodes. So the software can automatically insert new node, but I will leave this option turned off. And also I will use this option, set air release and washout valves automatically, meaning if this option is turned on, the program will automatically set air release and washout valves. And how this function works? So basically the function satisfied these rules, minimum, maximum depth, and minimum slope, but it is also optimizing and minimizing the number of inflection points. So let's check it. Let's select the entire network. Let's click calculate. And you see how this will be our position of the pipe. So let's click apply. Let's click save. And now take a look. This is the new solution of the our pipe position. And you can see that we have a lot less now amount of air release and washout valves. So the software placed our pipes to be on a range below the terrain between 1 meter and 2 meter, but it reduced the number of unnecessary inflection points. And it automatically placed air release and washout valves just on those places where they need to be. So let's check this node, for example, in plan. And here you can see, here we have a washout valve, here we have air release valve. But the total number of air release and washout valves is a lot less. So let's check here in our data table. Let's sort it again. And now you can see we have just 4 air release valves and we have just 4 washout valves. So really nice function for optimization of your pipe position with reducing the number of necessary air release and washout valves. Okay, and also I had some, I wanted to show you this procedure, how the number of air release and mud release valve is reduced. So, but this function can also be used even if you don't have the pipe elevation set at all. So you can have empty, empty profile, no definition of the invert or pipe elevations, and you can just run it from scratch. You don't have to have something to be optimized. You can just run it from the empty profile. Okay, so we are done with this example. I will save it so you can have it as well. I will call it just final, like this. And now we will go back to our main drawing, where we will now talk about setting water demands. So let's go back to our Hydra panel, and let's now talk about the function for setting of the water demands. In Urbano Hydra, you can set up water demands using many different methods. And now I will show you almost all of them, and then you will see what of those methods are good for you, what are useful for you, and which one will you use. So first of all, we have one method that we call percent calculation. And basically here in this part of the software, you can create any amount of these consumption categories, any amount of these demand configurations. So, and you have many different methods. So you can even combine different methods and then get the total calculated demands. So first of all, let's check this inhabitants in percent. So percent method. I will add a new configuration and I will call it people. So people living on this area, doesn't matter. And you have again your selection options. So you can set up where these demands will be set. So by default, you see the whole system is selected. And here you see that you can define water consumption per one inhabitant and actual number of inhabitant, or let's say number of people living on some area. So this is related to selection. So is it 1,000 people to the whole network, or let's say 1,000 people just to some parts of the network? So let's say that this main pipeline will be our main distribution network, where we will have no water demands, and then we will have our water distribution network where we will have our water demands set. Again, you have different selection options. You can use Urbano selections like branches and arrays, or you can use CAD selection. I will use this selection of arrays, and I will select this horizontal arrays and this for vertical arrays. So this part here, including these nodes on the main pipeline. So starting nodes on the main pipeline. And here I will say, okay, in this part of the network, I will have water consumption per one inhabitant per 1 day will be 180 liters per second per liters per day per inhabitant. And actual number of inhabitants, I will put it 5,000. Okay, population increase per year and design period. So this is the percentage each year the starting number of people will increase during the design period of 30 years. And we have our coefficients of variation. This is the coefficients to calculate the peak daily flow and coefficient to calculate peak hourly flow. You can define any coefficient. I will leave the default as 1.5. So like I said, during the 30 years design period, if each year the starting number of people increases by 2%, we will have at the end of the design period this amount of people, so 9,056 people. If you don't want to use this method of increasing the number of people, just define the design period to 0 or population increase per year to 0. And then if you multiply this number with the water consumption per inhabitant per day, you will get average demand per day in liters per day. Then if you multiply this with the coefficient of variation per day, we will get maximum demand per day. So this is the peak daily flow. Then if you also multiply it with coefficient of variation per hour, you will get the maximum hourly demand in liters per hour. And if we divide it by 3,600, we will get the maximum demand per hour in liters per second, which is our peak flow, maximum daily peak flow in liters per second. So 45 liters per second. Then we have selected this part of the network, which is in total this amount of meters. So 2,446 meters. And now the software is dividing 4245 with this number, and we have this specific demand in liters per second per 1 meter of the network, so 0.017350. And now this number is multiplied with each section's length, and we have a flow inside of a pipe. But in EPANET, and Hydra works with EPANET, to calculate hydraulic calculation, we don't need flows. We need water demand set, water demands defined in the nodes. So if we now calculate the flows inside of each pipe, here we have settings. So these are the default settings, how to distribute the flows calculated to the starting and ending node of each section. The default is half to every node, but you can also go with all to starting node or all to ending node. I will leave the default half to every node. Okay, so here I will now just click on write. So write, and all the demands are now set to our nodes. So we have the specific demands in liters per second per 1 meter multiplied with the each section length, and then that flow is divided half to starting node and half to ending node. This is the method how to calculate this water demands using this method. Also, like I said, you can create multiple configurations. Let's add one more, and let's call this one, for example, tourists, or any other type of consumption category. Let's call it that way. And now you can again select the same area or some other part of the area. For example, additionally, just on these parts closer to the sea, we have some additional tourists, let's say. And here I will set water consumption per inhabitant. Let's increase it to 250. And the number of tourists, let's set to 1,500. Okay, let's leave everything as default, these parameters. And now you can see the maximum demand per hour is 1769. This is the total length of sections, and this is the specific demand. So let's click write. So now we have two consumption categories with different parameters. Let's also check some other options that we have here. Here you can see something that is called calculate by branches. So let's now check this. Okay, let's create another configuration of this same type of calculation, and I will call it by branches. We learned yesterday what are the branches. So branches are basically everything in between two main nodes. So branch, 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 branch. Okay, so if I click here, calculate by branches, but I will select the same part of the network as before. So this whole network, like this, you can see here, I didn't change this, so I will set it to have the same values as for the configuration for the people. So we had 180 here, and here we had 5,000. Okay, and let's now check it. So here you can see maximum demand per hour in liters per second is still 42.45. Total section length is identical as before, and specific demand is identical as before. But now when I click write, so if this option is turned on, let's click write. Here you can see now, if you compare this column with this column, that it looks different because it is calculated by branches. So we have the water demands set only to starting and ending node of each branch. So why is that? Because as you know, in EPANET, you can have the, let's call them polylines, or links that consist of two junctions, starting and ending, and some vertices in between. In Urbano, we don't have polylines, but we have branches. So one branch can represent one multi-line pipe in EPANET. And basically, that's what we did here. So we distributed the same amount of flow, but just to the main nodes. And now this in between will be treated as one pipe. And you can see we have all other nodes in between are calculated as 0, because here in between we will have no demands. But if you summarize all these water demands, you will get the same value as for the people configuration. So that's how you can calculate this by branches. And also the procedure how to calculate it is basically identical. So you get the specific demand in liters per second per 1 meter, but now this is not multiplied with each section's length, but with the total branch length, and then that flow is divided half to starting node and half to ending node, but of a branch. Also, here you see something that is called corrected length of sections or virtual length. So what is that? Let's also analyze what is that parameter. Let's do one more configuration, and let's call this virtual length. This is nothing but a method how you can basically redistribute flows. So on some parts of the network you have bigger flows, and on some part of the network you have smaller flows, but for the identical number of people. So if we go to settings, here you can see that you can define population density factor. And here you can see that by default everything is not defined, which is absolutely the same as 1. So if it is not defined, it's the same as 1. So let's now use our selection options, and let's select here, just on this last array, let's set population density factor to 2. And let's click right. Okay. For this array here, let's define 0.5. Okay, and let's click right. And for this in between, we will leave it as not defined, which I said is the same as 1. Okay, so if I select now the whole system, you see that we have some are not defined, some of 0.5, and some are 2. Okay, let's now go to our virtual lengths, and let's again select the same. So we will select the same area as in the 2 previous configurations. We will set water consumption per inhabitant to be, we set it to 180, and actual number of inhabitants, let's set this to 5,000. Okay, everything else will stay the same. We have 42, 45, we have this total length of sections, but we have now total corrected length of section is different. Why is that? Because now these section lengths here are multiplied with 2, and this section lengths here are basically divided by 2 or multiplied with 0.5. So basically what we did, we virtually increased the length of this section and we decreased the length of this section. And in the final result, we basically set that more flow will go to these nodes and smaller flow will go to these nodes. But you see the maximum demand per hour is still the same. So let's click right. Okay, for the virtual lengths, and let's now compare it. So here you can see that you can see all the configurations, all the values, but you see that the one that is selected in the tree is marked in this cyan color. So let's, for example, analyze this part of the network. So let's analyze people and virtual lengths, and you can see that virtual lengths are much bigger demands. If we select this array here, you see that virtual lengths in comparison to people are a lot less. And also, if we select these two, you see that they are still smaller because, of course, we had that number, number total virtual length is now higher number. So if we divided the same peak flow with higher number of section lengths, we will have the smaller this data for the specific demand. So if specific demand is smaller, multiplied with the same maximum demand per hour, we'll have the smaller virtual lengths, the smaller demands, even though all the parameters are the same, and the population density factor stayed 1. So that's how all these calculations can work, and that's basically it. Okay, let's now go to settings, and let's set for the entire network this population density factor back to 1. So let's click right, and like I said, 1 is just like it is not defined, or you can click reset, it's completely the same. And also we have here one additional method, which is called inhabitants, but with Q specific. So let's add new configuration here, and let's select again the same parts of the network as before, these parts here. Okay, you see this is the total length of section, and total corrected length of section is now the same number. But now you can see that the software is not asking for number of people and consumption per inhabitant and so on. But the software is now asking for this specific demand in liters per second per 1 meter. So some of our users told us, okay, this method is really good, but we don't know the number of people. We don't know all these parameters here. We just get from some other guy who calculates all this. We have just this number. So now I will take just this number here, and I will go to this method. And here you can define it. So specific demand in liters per second per 1 meter of the network. Okay, let's set it, let's write it, and that's it. You basically have the same results as before. It's up to you, you know, which method you would like to use. But the thing is that let's check it like this. So if we select the whole network like this, and basically any of these data tables in Urbano, you can copy it. You can go to Excel or any other Microsoft application. You can just paste it, and here it is. So every preview functions that way. You can copy it to Excel. And let's now check this. So this is the tourists. This of course will not be the same, but if we check all these others configuration, let's sum this up. So if I sum the whole column, the total values should be equal to our peak hourly flow. Okay, so here we have that 42.45, and okay, 42.43. This is because of the rounding of the decimal places in the table. If we put to 6 decimal places, we will get the identical numbers. And the same is for this configuration here. So let's copy this one as well. So copy selected. Let's go to Excel. Let's paste it here. Okay, I will delete these columns. Okay, and let's do this. So you can see each time we get the same total hourly peak flow, no matter what method you are using. Okay, I will save this this Excel as well to our day 2 folder, and or here to day 2, let's save it as demands. Okay, that's these types of calculations. Also, we have the method to directly set the water demands to house connections. So this is really precise and really detailed method, but it requires that you first draw the house connections. We will talk about drawing the house connections tomorrow. So, but just for your information, you can even define point demands or number of people living in each house connection, and then of course those demands defined in house connections can be distributed to starting node of a section, ending node of a section, or even here it is, so half to every node, all to starting, all to ending, or all to closer node, because a house connection can be connected in between two nodes. So that's also a method, but we will not talk about it. Also, point demands. Basically, point demands are the basic ways how you can define demands in EPANET. I will call it, we can call it, for example, point demand, or if this is some specific type of demand, for example, I will call it industry, but it can represent everything. And now you have your selection options. Just imagine in EPANET, if you want to define some water demands, you have to go double click on one junction, type something in. Double click on another junction, type something in. Here you can select any nodes that you would like to set something. And for example, all these selected nodes will have the same amount. So let's say 5 liters per second. And let's click right. Okay. And now we have 5 liters per second in each of these nodes. Or let's reset it. Now we can go also to directly in data table. And for example, here it will be 1, here it will be 2, here it will be 3, here it will be 5, here it will be 7, and so on and so on. So this is really nice, really easy method how you can quickly define water demands by using this point demands method. Let's again reset it, and I will just go to this one node, to this node here, and let's say here it will be some kind of industry that has the consumption of 6 liters per day. Okay, this will be for our example. Then we have firefighting demands, but you see that the firefighting demands are basically under point demands branch, which is basically just a type of point demands. So you can add a new configuration. Let's call it firefighting. And now you can see that you have input type. Input type can be direct input, which is basically exactly the same as the point method I showed you. So let's, for example, select some nodes. Let's select this node, this node, this node, and this node. And let's set, I don't know, 5 liters or 10 liters per second. Let's click right. And that's it. Or you can switch from direct input to proposal for firefighting demand. Then this is grayed out, and you have this calculation, which may not be suitable for the whole countries, but a lot of countries has this standard where basically the firefighting demand is in relation to number of inhabitants. So for example, for 1,000 people, you have one simultaneous fire. Minimum duration for firefighting is 2 hours, and proposal for firefighting based on this number of people is 5. Let's check what will happen if I increase it to 5,000. Okay, for 5,000 people, we have still one simultaneous fire, 2 hours, and now the proposal is 10 liters per second. Or if I switch to 10,000 people, you see that the proposal for firefighting demand is 15 liters per second. So if we click right, now you see that this proposed value is written to each node in selection. And also we have something that we call pipeline own demands, which are basically, this can be treated as some quantities of water that, let's say, the water company spends on cleaning the pipes or some repairments on the network and so on. And again, for the input type, you can use it like direct input and define point demand somewhere under a different consumption category. But the real way how this can be used is if you go here to calculate own demands for every node in percentage of the previously defined demands. So you can increase the total flows in the network, let's say I will increase it by 2%. So 2%. And now you have to select by which of the previously defined demands. But here, just for the purpose of this training, I defined a lot of this configuration, but in some realistic workflow, it would be, for example, people, tourists, and industry, okay? And I will select the whole system. And now this flows will be increased by 2% of sum of people plus tourists plus industry. And let's click right. And now you can see for each node, it is increased by this amount of flow. Or this can also be used, the same method can be used also if you want to increase the total flows, if you want to account the losses. For example, let's add another configuration. Let's call this water losses. Okay. And again, I will go to calculate own demands for every node. And here I will say 20% of all the flows, 20% of what? Let's say again, people, tourists, and industry. Let's take into this also into account. So let's write it. And now you can see this will also be taken into account. So this is 2%, this is 20% additional flow. So these are now all the methods. I showed you all the methods. So now you can see, okay, this is cool. This is something I should use. This is something I will not use. But now you know all the methods. And even though you didn't find anything you like, you can still import water demands from some external source. For example, from let's say Excel file or plain text file as well. Of course, we don't need all these methods here, so I will delete them. But before I delete them, I will save this drawing, so you have this as well, all these methods. So I will call this Hydra demands. I will call it like this, save. And then I will again resave it as working 2. Okay, do you want to replace it? Yes. Okay, and now let's go to our water demands. Let's delete the configurations that we don't want to use. So by branches, delete, virtual lands, delete, inhabitants with Q specific, delete, firefighting demand, delete, pipeline own demands, delete, and water losses, delete. So we will have people, tourists, and industry, and this will be our basic water demands to calculate this water distribution network. Okay, so now we have everything set to run hydraulic calculation. So we have this water tank here. We defined it. You can also see that you can have, by default, it's not showing here, but you can turn it on in your configuration. So let's go to our configuration of the profiles. This one here is the one that we use. Let's go to edit. And here under longitudinal section basic, you have something that we call decorations. And here you can include it in the drawing. And you can see that you can define, it says manhole type dependent, but it's really node type dependent, because if you don't include this, you will have the same block for everything. But I like this option turned on. And now under details, you can define custom block, different custom block for each of this equipment. For example, for emitters, for pumps, for reservoirs, for tanks, for valves, and so on. So where is the tank? Here is the tank. We will use this block. You can also use some custom blocks, and I will use the scale factor of 2, for example. So we will have a larger block here. Let's click OK. Let's click OK. And now you will see that the block for the water tank will also appear here in the profile. Okay, so now that the water demands are set and the water tank is defined, let's now go and calculate this network. So Urbano Hydra uses EPANET engine, EPANET calculation engine, which is built inside Urbano Hydra to calculate hydraulic calculation. When I say it's built in, it means that you don't have to have EPANET on your computer at all, because the EPANET code is built inside of Urbano Hydra. But you have to know that basically EPANET is doing all the calculation. Urbano Hydra is here for drawing of the network, setting the parameters, setting the equipment, and then when you click on calculate, you can also define all the EPANET options. You see here hydraulic options, times options, energy options. I will leave everything as default. And each time you click calculate, EPANET EMP file is created and you have all the results. So basically, EPANET EMP file is created. In the background, it is sent to EPANET engine code, which is built inside of Hydra. EPANET calculate all the values, and you have all the values here back in your AutoCAD familiar user interface. And you see that I already told you yesterday, when something is blue, it means that it is newly calculated. And also, this is a really nice feature because I just clicked calculate. I didn't click save yet. You see that we have the old values shown first, and the ND means not defined, because before we had nothing, we had no results, and now we have these results. When you first click on calculate, it doesn't make much sense. But later on, when you change something and when you click calculate, you are able to compare the old value with the new value. I will show this later. So let's now just click on save. And here you can see flows, velocities, head losses, unit head losses, statuses, and so on and so on. And also you can switch to preview for the nodes, and you can see the total calculated water demands. These are the head elevations, these are the pressures, and also the statuses, but they are blank because we don't have any pumps and valves defined yet. Let's switch to section preview. And also, I said that you don't have to have EPANET installed on your computer at all. But here is the EPANET EMP file, which is saved in your working folder where your drawing is saved under this file name. And if you have EPANET or basically any other hydraulic modeling software, because EMP file is standard for hydraulic modeling software, so you can go with this EMP file, let's say to EPANET, of course, but you can also go to I don't know, Bentley WaterCAD, you can go to InfoWorks, so any other software that you use. So EPANET EMP file is basically world standard. But I will of course use it in EPANET, so let's click open. And here it is. This is the same network, exactly the same with everything defined. So let's click, for example, on this node here. You see the names are as defined in Urbano. You see these demand categories. It says 3 demand categories, which are basically the configurations that we created in Urbano. So people, tourist, and industry. Or for some other node, here we have 2 demand categories, just people and tourists. Also, here you see the elevation, which is basically the elevation. What I, yesterday I talked a lot about this. In Urbano, we have terrain elevation, we have the pipe elevation, and then pipe can have 5 points. Top of the pipe, the top inner point of the pipe, center line, bottom inner point of the pipe or pipe invert, and the bottom of the pipe. But in EPANET and all other hydraulic modeling softwares, you just have elevation. So what is this elevation? So this is that center line elevation, So that's why I used the center line. Okay, and demands are here also. If we check, for example, the pipes, you see here the lengths, the diameters that we set, the roughnesses, everything is here. Also the names of the pipes as well. Okay, let's close EPANET. We don't need it because we have everything here in Hydra. And let's now check the results. So you see that the profiles automatically updated with these piezometric lines showing us the head elevations. And you can see that the frame of the profile didn't automatically expand. So to solve this, just click here on redraw the profiles. And now the frames updated as well. So you can see that we have our piezometric lines showing the head elevations, and also we can go to plan as well. And maybe we can now put this hydraulic values also to our labels. So let's now change the label configurations. We talked about this yesterday, how it is easy to just change the label configurations. We can repeat it. So for example, for the sections, I will use diameter, flow, and velocity. You can double click on it, you can select it, you can click on mark, or you can make this as default. So let's set this as default. And also for the nodes, let's use name, demands, and pressures as default. And now I will run these commands for the entire system from the ribbon. Okay, for the nodes, for the sections. And now you see for the nodes, we have the node name, total demand, pressure, and also here you see diameter, flow, and velocity. And also we can check these labels to see if all the velocities are okay, if we are satisfied with this. So you can check this using the labels, but of course we have our data tables. So let's again open the data tables. Let's use our mark in plan option so we can see which sections are selected. And let's switch to section hydraulics. Okay, let's check the velocities. Let's sort it by, first of all, let's select the entire network. Let's sort it by velocities. You see that we have some very small velocities that are marked in red. And now I will show you why they are marked in red. It's not that it's some kind of error. It's just something that we call data validation. So inside of each configuration of data previews, for example, we are using section hydraulics. Let's go to section hydraulics. Here you can see this validation type. And you can see that for the velocities, this checkbox is turned on and it says validation type is between 0.10 and 1.5. You can change this at any point. And other validation types are, for example, greater than some value, less than some value, not in between, or also for some textual values for the strings. If contains something, not contains something, is the string equal to some string, and stuff like that. But this is the one that I like to use the most. So between 0.10 and 1.5. So if the value is outside of these ranges, it will be marked in red, or you can also define this color. I like to be red. So here we can see now where we have some velocities that are maybe too low. And also if we sort it by highest velocities, we can see where we have some pretty high velocity, higher than 1 meter per second. So it's in this part of the network here. And of course, in these parts of the network, we have the highest velocities. But if you remember yesterday, we defined these pipe diameters pretty roughly. I was just showing you how you can set up the diameters. And now, of course, if you want to just change the diameters, let's say on these parts here, we can select these diameters from the table. You can right mouse button on it and you can click on edit data. When you click on edit data for pipe diameters or pipe materials or pipe related data, automatically the software will open the function for setting the pipes. So let's go to edit. Okay, and these pipes that are selected in the data table are automatically selected now in this dialog, and now we can increase it. For example, here I have 200. Let's select from the same pipe group. Let's go, I don't know, with 250. Let's click save. And now you see that the data table automatically updated. Here is the inner diameter shown. Here is the nominal or outer diameter shown. And here you can see how the style also automatically updated, showing us here the bigger diameters, realistic pipe dimensions. So this is the, let's say, manual process, and you see that the velocity didn't change automatically. We have to go again to hydraulic calculation. We have to rerun the calculation, and now you can see this old values, new values. So let's select just this branch here, and now you can see before the values for the velocity were 188, and now it will be 134. So you see here 188 was before, and now it will be 134. So let's click save, and now you see that this is changed as well. But I think this is still too much. So even though it is not marked in red, because here under section hydraulics, we define that the top value will be 1.5, but I think these velocities are still not good enough. This can be much better. Also, another great way how you can analyze these values, not by using data tables, is by using thematic mappings. So here we have the theme mappings. Again, from the installation, from the country kit, you will get all the defaults for the arrays, for the branches, for the diameters, for the velocities. We can check it. So for example, for the arrays, let's select the entire network, set legend position, let's click show, and this is now theme map for the arrays. That's how we defined the array definition yesterday. Okay, let's now check something else. Let's delete this one. Let's check the diameters. Okay, show, and let's place the legend here. So this is how we defined the diameters yesterday. So of course, all these color ranges can be set up in the configurations. We will show later, I can also create one of the theme maps as well. So this is now the theme map in different color for the diameters. Let's delete this and let's apply it for the velocities as well. Again, we will set the legend position, and this is how our velocities look like. And you see that this orange part is between 125 and 150, and we have pretty high velocities in this part of the network and pretty low velocities in these parts with the dark blue color. So let's open, for example, this one for the velocities. Let's click edit. And here you can see that you can choose the data according to which you would like to create the mapping. You can define these ranges. You can define it by defining number of limits or size of the limits or this ranges. So here for the velocity, I defined custom ranges. First we go by 0.25, then I go by 0.5. So you can basically define any ranges that you would like to see. Okay, so now that we checked the velocities, let's try to optimize these pipes. So to do that, we have our pipe optimization function on the Hydra panel. It's called pipe optimization or initial pipe selection. So you can optimize the existing pipes that you defined by yourself, or you don't have to have pipes selected at all. You can just run it for the first time and get the optimal solution. We will optimize the existing pipes. So here, first of all, you can create some, again, configurations, or it's better to say maybe zones or groups, because if you just, I don't know, here you can select the total the whole catalog. You here can define the target velocity, and if you click start, of course, you will get results. The results will be pretty good, much better than what would you define manually. But if you want to decrease the time necessary for the software to compute, and if you want to increase the quality of the results, if you want to get as great results as possible, then it is recommended to create some groups. Now I will show you why. For example, let's create one group, and I will call it transport pipeline. Okay, Here you have your selection options. So you have to define which parts of the system will be assigned to that group. Let's go by arrays and let's select this array. Okay, so here we have this part of the network under this group. Let's create another group, and here I will call it a distribution network. Okay, let's now select these parts of the network here. You can also use CAD selection to select it more easier. Okay, and now you see that in the default configuration we have 0. So basically we define 2 new groups. And now for each group, you can define what is the target velocity. So basically how this calculation works, you define a target velocity and the software is using genetic algorithms to find the diameters, to find the pipe diameters so that the real ending velocity in those diameters, in those pipes, is as close as possible to your defined target velocity. And now, for the entire group, you can define single target velocities. For example, let's say for this group, it will be 0.9. And for this group, because this is the distribution part of the network, we will have smaller velocities. Let's say the target velocity will be 0.6. This is one way. Or you can use this diameter dependent, which is the option that I like to use, because now for each range of diameters, you can define the target velocity. So now the calculation will be a little bit more complex, because for each calculated diameter, the software will check its target velocity. So for example, if the pipe is between 0 and 100, of course, you can change and define these ranges. Then target velocity will be this, target velocity will be this, target velocity will be this. So this is the option that we will use. So for this group, diameter dependent, and also for this group, diameter dependent. Also, for each group, you can define which pipes can be used from the pipe catalog. This is what I said before. You can, nothing is stopping you, to select the entire group. So we will use this PhD pipes. You can select the entire group. But then in this group, I have the pipes from 32 millimeters all up to 1000 millimeters. And of course, I know that here, for sure, I will not have pipes, let's say, smaller than 200, for sure. And they will for sure not be bigger than 400. I don't know which pipes are optimal here, but based on some logical thinking, by doing this selection, I reduced the time for the software to compute, and immediately in the start, I removed some solutions that are basically not solutions, because they are really bad solutions. For example, if you take pipe of 32 millimeters, the software will try to see where this pipe can go, and it will just take time to compute something that is not useful. So this is something that is recommended. It's not mandatory, but it's recommended. And also now for this group here, I will do the same, but here I will select smaller pipes. Again, I don't know which pipes are necessary, but let's go, for example, from minimum 1.10 to, again, I will select 200. Okay. And also here you have some advanced options. You don't have to change the defaults. I like to change some stuff here. So basically how this works, like I said, it uses genetic algorithms, so mathematical method. So here you can define some parameters. For example, the initial population size, I like to increase this to 500. It will not take that much time, but it can increase the quality of the final solution. Also, if the velocities are too high in the network, the software will treat those solutions as bad. So here you can define overspeed penalizations. And I don't like my velocities to be over the target velocities that I define. So I like to increase this over speed penalization, let's say to 1. And also under speed penalization, okay, if you, I prefer to have a little bit larger pipes than a little bit smaller pipes, but because if you have a little bit smaller pipes, then the velocities will automatically be higher. So also I like to decrease this to, let's say, negative -1. Okay, here are also some advanced options that can be changed or not. For example, number of generations, let's increase it to 500, mutation size and number of crossover points. So these are just some mathematical parameters. But of course, if you increase these values, you will get more, let's say, quality solutions. Let's click Save, and now let's click Start. And now you will see how the software is searching for optimal solution, because that number that we set, initial number of generations, 500. So the software randomly put 500 possible combinations of these diameters and send it to EPANET. And then EPANET calculated, results are back in Urbano, and now we are checking, okay, this result is better, this result is worse. And in 30 generations, the software calculated this, and we see that the fitness factor is 0.16, which is great. I know, but just by checking this number, this is great. So let's check it. For example, let's select this array here. And again, it is not saved automatically. You can check the results. So these were the old results, the low, the small diameters that we had before, and now this is the results given by the software. And again, you see the resulting flows, velocities. These were the target velocities, and this is the difference between the real velocity and target velocity. Let's save these results. Okay, and let's now check this. The target velocities were around 1 for these diameters, around 0.80 for these diameters here. And now the difference between the real velocity, ending velocity, and the target velocity basically defines this fitness factor. So of course it is impossible that your target velocities and real velocities are completely equal, then this fitness factor would be 0, but that's really impossible. So we can check the other results as well. I think this is really good solution, and basically that's it. If you're not satisfied with something, you can continue editing and increasing or decreasing pipes, but I think that this solution is really great. Okay, let's close this, and let's now check our results. So you can see that the piezometric lines changed a little bit. We have here now much more smoother transition, which means that we have smaller head losses. So the piezometric lines look really good. Let's now check our data tables again. Let's check it for section hydraulics. Let's select the entire system, and let's sort it by velocities. And now you can see that we have a lot less these red numbers, only 4. And this is the ending parts of this branch network, these dead ends. So this is something that should be expected, but I intentionally didn't go with the diameter smaller than this, because later on we will also include some firefighting demand as well. And if we check the highest velocities now in the network, it's 0.99. So now we have the higher velocities in these parts of the network, and they are smaller than 1, which I think is great for this network. Let's also use T-maps now to check the results. Again, let's apply one T-map for the velocities. Let's show it, and let's place it here. And now you see we have much more green color and much less of orange and red color. So I think that now the velocities and diameters in our network is really great. Okay, so we sized our network. Let's also now check the pressures inside of this network. Let's delete this T-map for the sections. Let's again open our data tables, and let's check for the node hydraulics. Again, we can check these red values. If we go to our data table for the nodes, node hydraulics, let's edit this, and you see here, calculated, no, not this, but this, starting pressure and ending pressure. You see that we have the minimum and maximum values for the pressures for this validation defined as 25 and 70 for the minimum and maximum pressures in the meters of the water level. So 2.5 and 7 bars. Let's check it here. So we see that the smallest pressures are basically in this part of the network here, which is basically outside of the populated area. This is, as you can see here, this marking options. So this is close to the water tank. So this is not a problem. But let's check the highest pressures. And we can see that the highest pressures, pressures higher than 70, are located in the bottom part of this network. But of course, that was expected because we can see the terrain difference in this terrain here is pretty high. So of course that we will have a lot of pressures here. Again, let's use T mappings to check these pressures in the network. So I will apply one T map for the pressures. Let's select the entire system. Let's set the legend position and let's put it here. And now again, you can see these color ranges that I defined inside. You can open it, you can edit it. These are the defaults, so I didn't change anything. So by default, you have these colors going from colder colors to warmer colors. So it goes from 0 to 100, but of course you can add additional pressures as well. So this is the legend. And now we can see where we have these really small pressures and really high pressures. Another great function to analyze this is drawing of the contours. So you can draw these contours by using, again, this predefined configurations, or you can create your own. Let's check, for example, this gradient. This is really nice because you don't define the ranges for the colors. You just choose this color stylist gradient, and it will automatically go from the red values for smaller values to blue values for higher values. So let's just draw it. And now you can see we have color gradient from colder colors to warmer colors. But now you can see that these ranges are not matching completely. They are matching, but they are not matching completely this legend here. So if you want these contours to match your configuration, you have to use the custom color ranges, so custom color ranges, and you can set up, just like for the T maps, you can set up the same color ranges and define the same colors as for the T maps, and that is the default. So let's close this. Let's first delete the old ones, and let's apply this pressure custom. Let's draw it, and here it is. Now you see that we don't have the gradient anymore. We have the strict transitions from blue to cyan to green to orange to red. And also it is important to say that these are basically like terrain contours. These are 3D polylines. And if you switch to 3D view, you can also check it in 3D as well. This is basically like a DTM, but not with terrain elevations, but for the pressure elevations. But basically inside of it, you can also choose different data. It doesn't have to be pressure. It can be head elevation, it can be terrain elevation, it can be invert elevation, and so on. Okay. So now we basically come to a conclusion that here would be a good place to place one pressure reducing valve. So let's delete the T map. Let's remove the pressure contours, and let's now set one pressure reducing valve to this node here. So to do that, let's go to Hydra panel. Let's go to hydraulic node equipment, and here let's set a valve to this node here. Like I said, you have all the EPANET available valves. So you can use, for this case, you can use pressure reducing valve or pressure breaker valve. And I like to use pressure reducing valve. So for the reduced pressure setting, I will go to, let's say, 35 meter of the water level, so 3.5 bars. Let's click apply. You see how the graphics automatically changing. You can also click here on redraw or reindex for the style to update as well. And now you can see that this will go up to the edges of this valve. And also if we go to our profiles, you will see that some graphics will also show here. So you see this is a custom block for pressure reducing valve. Also here we see that the profile for some reason didn't update correctly, because you can see we increased the pipe diameter and the trench remained here. But this is not an error. This is just the profile, the trench didn't automatically update. So again, if you see something like this, just click on redraw profiles, and in a second you will have this. So if we check the results now that we applied a valve, again, nothing changed because we have to rerun the calculation. So let's open hydraulic calculation again. Let's click calculate. Let's save the results. And now you can see that the pressure dropped from 67 to exactly 35 meters. So now if we check our profiles, you can see this pressure drop happening because of this pressure reducing valve. Okay, so now we resolved the pressures. We can also reapply the team map. So to check it once more, let's go to pressures. Let's show this team map and place it here. And let's also repeat our contours for the custom pressures. Let's draw it. And now you can see how these colors look much better. So we do not have the red values. We have only the green, cyan values, and also some of the orange values here around our pressure reducing valve. If we open our data tables and now go for node hydraulics, let's check it. Let's select the whole network. And now you see that the highest pressure in the network is 67 meters, which is here just before this pressure reducing valve. Okay, let's delete the team map. Let's delete also this drawing contours. Okay, and basically now we have our final results here, so we can also check it. And one really nice way how you can check it, I didn't show this, but marking plan, we use it all the time. But here you also have zoom in plan, which is really nice. So you can select, for example, I will select this array here. Let's use zoom to plan. You also have zoom to profile. Let's zoom to plan. And now you have marking plan, but we are under nodes. Let's switch to section hydraulics. And now you can see that for each section, you have values written in the labels, and also you can simultaneously check them in the data table as well. And you can see standard data for the sections like diameters, flows, and velocities, but also you can see for each section starting and ending pressures as well. We can also add the piezometric line or head elevations to labels also. But by default, it is not, because the pressure is maybe enough to check this here. Okay, now I would like to show you how to work with scenarios. So let's again open our water demands dialog. And let's create one more point demand now for firefighting demand. And let's call this fire, or let's call this fire 1, for example. And let's create one more, and let's call this fire 2. So if you set multiple firefighting demands into same configuration, that would mean that you have parallel fires. So if you want to simulate firefighting demands on a different parts of the network, let's say different hydrants being active, then put them in a separate configurations. For example, for this configuration, I will set one firefighting demand of 10 liters per second here. I will use data table to set it. And for this configuration, let's set firefighting demand of 10 liters per second to this node. Okay, let's now create scenarios. So I will create 4 different scenarios. You can create any amount of scenarios. These are water demand scenarios. So let's say first scenario I will call winter. Second one I will call summer. The third one I will call summer plus F1 like fire 1. And the fourth one I will call summer plus F2, which is fire 2. And now by default, everything is turned on. You see these check boxes, you see the blue values, the blue columns in the data table. But for the winter scenario, first of all, I will turn off firefighting demand. I will turn off the tourists. So we have only people and industry. For the summer, I will turn off firefighting demands. For the summer plus fire 1, I will turn off fire 2. And for summer plus fire 2, I will turn off fire 1. Now we have 4 different water demand scenarios. And now we can go to scenario preview. And basically, here we can compare different, basically we can run parallel hydraulic calculations. So let's check it. Let's turn on summer. Let's turn on summer plus fire 1 and winter. And now you can see data by data or scenario by scenario in different colors, all the results for that scenario. So red is summer, yellow is summer with fire. You can see how the flows are bigger because we have additional 10 liters per second for fire, and the blue is winter. So you can check it like this, or I prefer it to check it like this so you can immediately compare flows, velocities, head losses, unit head losses, everything is here. And of course, you can also switch to data table for the nodes and compare. Here are the water demands, here are the head elevations and the pressure elevations. And just like for everything in Urbano, you don't have to analyze the whole system at once. You have your selection options. So for example, you can select just this array or just these 2 arrays, and then analyze just that part of the network. And you can see in the yellow scenario, which is the scenario with firefighting demand, we have this higher velocities because of the additional 10 liters per second. So like any other data table in Urbano, you can select it, you can copy it, or you can copy it as HTML, which means that also all these colors will be copied. So let's copy. Let's go to Excel. And here, let's just paste this. And here it is, one really nice report with all these colors copied. So here you can see that for these sections, for this scenario, you have this really, or let's say higher velocities because of the firefighting demand. So that's about it about water demand scenarios. I will also save this report. So let's save it here, and I will give it a name scenarios. Okay, and click save. Okay, let's close this and let's go back to Urbano. So now we have scenarios. So now when you go, for example, to hydraulic calculation, here the software is asking you, okay, calculate, but according to which scenario? That I showed you before is just a table the software calculates everything on demand and shows in that table. But as you can see, the results didn't change. The results are still saved for that scenario without firefighting demand. So default is sum of all defined demands, which would be, if I click calculate, you see it's 86, meaning 2 firefighting demands. And you have all of the scenarios here. So for example, let's save the scenario with 1 firefighting demand. Let's calculate. Now you see it's 76.14. Let's save it. And now this one is saved in the model. So that's how you can switch between the scenarios. And you can see because of the firefighting demand, we have this pressure drop happening on this part of the network here. And we can also check this higher velocities. So here it is. This is the velocities of 1.5, 1.4, and so on, 1.6 here. So we can check it in the data table. Let's select, for example, this branch here. And here you can see that I will turn off auto zoom. Here we have the higher velocities. Of course, now you could go again to our pipe optimization. And now you will also see here that for demands, you have, just like for the hydraulic calculation, you have sum of all defined demands or according to one of these scenarios. So now you can rerun this calculation and get different or better pipe diameters, but I will not repeat the procedure now. But also I would like to show you this. Sometimes, of course, you will have the overlapping of the labels. You will have overlapping of the labels with the sections or with the nodes, or one label with another. So of course you can move the labels interactively by starting the function move label. You can select the label that you would like to move, select the base point, and basically move that label. Or the option that I prefer is the automatic label reposition, where you can define what labels you would like to automatically move. Let's select just the node labels, and then you can define the rules for moving. So how this calculation works. First of all, the software is rotating by some angle. Default is 30. We can leave 30, or let's say 22.5. So the software is rotating this and finding the position where it won't be in intersection with the elements or with another label. If this cannot be satisfied by making a full circle, then the software will increase the leader. So it will increase a leader by this value. I will set by 1 unit. And then if it again makes the full circle, it again goes the full circle, this time of iterations or trials. I like to increase this to, let's say, 1000 or 2000. It's very quick, so it doesn't matter. And also you can also put some buffer around the labels so that the labels are not too close one to each other. I like to put 0.5. Select this whole system. Let's click here. And now you can see 5 labels are automatically moved. So there is no overlapping of the labels anymore. So really nice and powerful function. Here we have just 5 labels, but just imagine if you had to move 500 labels. Okay, so let's now continue. Now I would like to add an additional part to this network. And here I have, okay, I don't have here, but I have it here in the layer manager. I have the pressure pipeline layer that I will turn on. Okay, so now we will a little bit repeat what we talked about yesterday. We will draw one additional part of the network, and we will set up a reservoir, a pump, and this will be a pipeline from the pump to the tank. To convert this to, because this is just plain 2D polyline, I will again use conversion of CAD elements. We will use the same DTM as yesterday. The center line will be 1.5 meters below the terrain. We can use the labels. I will use the same labels as we have currently in the drawing. And I will select this polyline here and convert it to intelligent Urbano topology. Okay, let's now draw the profile for this new part of the network. I will use the same profile configuration. Let's go from node to node. I will go from this node here through this node here, all up to the last node of the system. Okay, let's now place this here. I will again use the extension and put it 50 above this one, like this. And here you see that for this part, from the water tank to the last node, we have the piezometric lines, we have everything calculated, and here you see that we don't have anything defined yet except for this center line elevation on a constant depth below terrain. Let's now first define the pipes. I will set the same pipe diameter that we have here, and to do that, I will open the function for setting of the pipes, and here I will select this array like this, and then I will use this match properties, this really nice option where you can select the pipe from the drawing, like let's say this one here is 355, and the software selected that pipe here. And now when you click save, this pipe, the same that is here, will be applied here. So we set the pipe now. Let's continue. I would like now to show you the dynamic model of Urbano. So I will split my screen now so we can simultaneously see both plan and the profile. So this is this part here. And you can see that we have these nodes on a pretty high distance, and this pipeline is not following the terrain as good as it can. So I will now insert some new nodes. You can insert new nodes in plan or in profile. Now I will show you both ways. First of all, let's go to Urbano layout, and to insert new node, I will use this interactive function. This is really nice function because it allows you to edit nodes or sections. If you click on a node, you can change the type of the node, you can label it, you can move it, you can delete it, you can rename it. Or if you click on a section, you can add new node on a section, you can label it, you can delete it, or you can rename it. We would like to add a new node on this section, which is this section here. So let's click here, and now you can see that you can add a new node anywhere, or if you press Ctrl button on your keyboard, you will be locked to that section. So let's click, for example, here, and you will see the software automatically inserted the new node here. So now this section is split into two sections, and here we have one new node here. Also, we can add new nodes directly in the profile. So let's check that now. Let's go to profile ribbon, and let's use edit nodes. And here I will go to insert. You can also move or delete nodes directly in the profile. I will go to insert, and here I will add some new nodes. So for example, let's add one new node here. Let's add one new node here, maybe here as well, or here. Let's add one new node here. Okay. And now you see the new nodes automatically appearing in the profile and in the plan as well. So you can see how they are called some PN so that you can recognize the new ones that have been added. And you can see the same nodes in the profile as well. Okay, let's now rename this new array that we defined. So let's go to editing, edit of the arrays. Let's go to rename automatically, and let's select this one here. I will give it some prefix. I don't know, let's put a prefix T, apply. So it will be a T1. Okay, let's now also rename the nodes. Okay, I will use the function for renaming by arrays. So I will select this array but also this array as well. If you remember yesterday, if I select just this array here, it will be renamed, all the nodes will be renamed. But I don't want this node to be renamed to, it will be T something, the last node of the T array. This is why we have this sorting. So if I say A1 is in front of T1, then this one will be main. So let's say as a prefix, again, just like yesterday, I will use the name of the array like this. And now if we click on apply, you see this one will rename A11, and all the other ones are now T11, T12, T13, and so on. Also, you see that now this, again, these nodes are, these labels are intersecting with the elements. So we can also rerun automatic label reposition for the entire network. Let's run it. Additional 7 labels are automatically repositioned. So now you can see how it looks automatically much, much better. Okay, and let's also rename the sections. So let's go to renaming of the sections. Let's select this array here, and let's use the pattern. If you remember from yesterday, monkey 5 is for counter. So I will say, let's say T with the suffix monkey 5. So it will go from T1 to T10. And let's click apply. Okay, so we define now the new nodes, but you see that the pipe is still on the same position. The pipe didn't move, we just have new nodes. So now that we have new nodes, we can go again to input data, invert elevation, and let's set now for this array here, this new one here, let's set that the center line is again 1.5 meter below the terrain for each node. Let's click save. And now you will see that now we have our pipe that is following our terrain much, much better. Okay, so we defined that. You can see that also we didn't set the trenches and the top layers, so we can set up that as well. Let's repeat from yesterday. Let's go to trenches. Let's select this array. Let's set the same trench as yesterday. Let's click save. Okay, let's go to setting of the upper layer. So input data, upper layer. I will use again the soil of 20 centimeters. Let's select this array and let's click save. Okay, and now we have everything defined. Okay, so now as we see here, we have to also define reservoir, pump, and that's it. So let's now go to Hydra panel, hydraulic node equipment. Let's select the first node in this system, this one here, and let's set it up to be a reservoir. And let's click apply. You see that a custom node appears in plan and also here in profile as well. Let's also set a water tank, a pump. So let's go to hydraulic node equipment. Let's select this node here. And let's set this up to be a pump. For a pump, you can use a pump curve or pump power. I will use a pump curve, but we have to define the pump curve, so we will do that now. Let's click apply, and you see that the pump is set, and again, you see the custom block appearing in plan and also appearing in the profile as well. Okay, so now that this is defined, we can switch back to having just one view. So let's do it like this. And let's now turn off this helping layer. We don't need this anymore because we converted everything to Urbano. So let's turn off pressure pipeline. Okay, let's now define a pump curve. How to define a pump curve? So we have to know a flow and the difference between the starting and ending pumping elevation. So let's check this. Let's open the node geometry And let's select this node here from the pump to the tank. Okay, and this is the physical difference in elevation. So if we open the calculator, we will have the 103.36 minus 36.56. This is 66.8. But also, if you remember, inside of our water tank, we defined the starting initial water level to be 3 meters. So I like to include those 3 meters in the pumping elevation as well. So the pumping elevation will be around 70 meters. And also what flow we are going to pump. So as you remember, we have the flows already calculated. This is the 76.14, but if you remember, this is with firefighting demand. So it's up to you to define a pump curve. So define curves and patterns. Let's define here. You click just like for defining a new catalog of pipes or manholes or anything. Create a new group. You can give it a name. I will call it pump curve. Then choose here the type of the curve. It will be a pump curve, and then create a new item. Here it is, and give it a name. I will call it, for example, pump 1. And now you click here to set curve data, and here you can define the flow and the head. This is just like in EPANET. Basically, you can define 1-point pump curve, 3-point pump curve, or multiple point pump curve. I will keep it simple, and I will say, okay, our flow without the firefighting demand is 66.14, and our pumping head is 69.8. Of course, you can round this number or define your own pump curve. This is just for this example. You have to click here to add. And now you can see that the software is, so this is the working point of a pump, but the software is also extrapolating all up to flow of 0 to the head of 0. So this is the pump curve, and this whole range of flows is covered now. Okay, let's click OK. Let's click OK. Let's now go to network element data. This is a function where you can see all the set network elements in the drawing. So we have a reservoir, and you can check all the data for those elements. So reservoir, we have a tank, we have a pump, and we have one pressure reducing valve. For the pump, so you don't have to go again to hydraulic node equipment because the equipment is already set. We have a pump already defined. So you can just go to network elements data, and for already set pump, you can set the pump curve, for example, to pump 1. And let's click save. Okay, let's now calculate this. So let's open our hydraulic calculation. Okay, so let's go to hydraulic calculation. Again, we can choose according to which scenario. I will leave this summer plus fire 1. Let's click calculate. Let's click save. Okay, and now you can see how we have calculated this part of the network as well. So we have our pump, adding the pressure to our network, and here we are to our water tank that we had from before. Now, let's also define one time pattern. So let's go to the same function, define curves and patterns. Here, let's define a time pattern. Let's add a new catalog group. Let's call it time pattern. And let's create one new time pattern. Okay, let's call it people. Under geometry data, we can define by default it's 24-hour, but you can also increase the number of hours or decrease the number of hours and set any number of hours. We will define one 24-hour time pattern. So for example, during the night, let's start with smaller values. Let's say 0.5, 0.6, 0.7, I don't know, 0.8, 0. 9, 1, I don't know, let's go now to 1.1, 1.2. Basically, so now let's say that this is a smaller town. So during the night we have smaller values, and now during the day when people go to job, the number is increasing. So basically we are defining maximum peak factors. Okay, now maybe let's reduce it back to 1.1, then maybe 1, 1.1, 1.2, 1.3. Basically you define it like you think it is applicable for the area that where you are designing the network. And now let's say we have our peak flow of the day. Let's say at this point of the day people will come home from work and I don't know, have lunch and so on, and this is maybe our peak flow. So 17th hour of the time pattern, which is from 4 to 5 p.m. And now I will start dropping, let's say 1.4, then maybe 1.3, again 1.3, 1.2, 1, and let's finish it with 0.8 and 0.6. So this will be our time pattern for this network, for the people, and let's say for the tourists. And let's also create one additional time pattern, and let's call it fire. I will call it fire, and I will set one firefighting demand during these same hours, that we have our peak flow, and I will just say 1. So from 4 to 6 p.m. we will have one firefighting demand lasting for 2 hours. So during our peak flow. Let's click OK. Let's click OK. Let's now set this defined patterns to our water demands. So we are opening back our dialog for water demands, and let's go here to people. And here you can see that we previously, to size our network, we already defined our coefficient of variation per hour. So be careful, don't just add now this time pattern here. So under pattern, I will select people, because now this pattern will multiply these values here. So you will just be multiplying it again with the peak hourly factor. So we have to set this coefficient back to 1. So let's again select the same parts of the network. You can also create some selection sets, so you don't have to repeat this procedure of selection all the time. So here I will switch this back to 1. You see now it's 0.4, but if I write it, now it's 0.27. So we reduced this back to 1 because now we would like to have a time simulation with this time pattern. Let's repeat this for the tourists. So let's assign the same pattern, people, and let's repeat the procedure. So this, and this will have coefficient of variation per hour 1. So now is 44. Let's write it. Now is 0.29. For the industry, let's say that this industry is using this 6 liters per second during the all 24 hours of the day. So I will not be setting the pattern. And for the firefighting demands, let's set here fire pattern. And for fire 2, we can also set the fire pattern. Let's click close, and let's now go to hydraulic calculation. So let's go to hydraulic calculation. And here now we will go to options, and we will switch the total duration from 0 to 24. So we will do simple time simulation lasting 24 hours. Let's click calculate. And now you will see that we will have much more results than before. We have 32 sets of results. So not just 24, because something is also happening in the between hours. And now we will analyze what. So let's save this results. We calculated according to summer plus fire 1 scenario. So we have just one firefighting demand in this node. Okay, so here you can now check all the values, and you can, with these arrows, you can go through time. So midnight, 1 o'clock, 2 o'clock, 3 o'clock, or you can move with this drop-down list to a certain point of a day. Let's say, let's switch to our 4 o'clock where we have our peak flow. So you see 7614, our peak flow, and also you can use your selection options. So let's select maybe just this section here. And here you can see that this is the flow of 1038 with our firefighting demand. Also, you can switch to a time preview for that section. And now you can see for all the periods of the day that at these points here, we have our flows of 1038. So basically during the whole day, we have very, very small flows, but during these 2 peak hours, we have much bigger flows and much bigger velocities. But the best way to analyze always these time results are by using the graphs. So let's switch to graphs. And now here you can select any data that you would like to analyze, and you can do it 2 times. So for data 1 and data 2. For example, let's select this node here where we have our water tank. And now you can see that why we have this multiple results, not just 24, because as you remember, our water level is starting from 3, it's rising until it reaches 6, and then the water tank is full. Now here for velocity, let's also select this section right after the pump. And now here you can see that when the water in the water tank reaches the maximum level, which is 6, the pump closes. So the pump closes, the velocity after the pump is 0. And this is constantly turning on or off because we didn't define any rules when the pump to close and when the pump to open. So the software is automatically turning on and turning off the pump when the water level is it reaches maximum water level. So what we can do now, let's say we can go to network elements data, we can go to our water tank and basically just increase the maximum water level. But this is maybe not realistic. The right way would be to create rules. So let's create some rules here. I will create 2 new rules. First rule, I will call pump off, which will close my pump when. So here I will select this water tank and I will say if what water level in the tank is higher or equal than 5, then what? Select this pump. So then this pump status will be closed. So if water level in the tank is equal or higher than 5, then pump will be closed. Okay, the second rule will be pump on, which will turn the pump back on. So let's now again select this water tank. Okay, and I will say if water level in the tank is smaller or equal to 1, so we will not allow the pump to go to the water level in the tank to go below 1, then what? In this pump here, the status will be open. So if water level in the tank is equal or lower than 1, then pump status will be back open. Let's click OK. And let's now rerun our hydraulic calculation. Let's go to hydraulic calculation. Again, it will be time simulation of 24 hours. Let's click calculate. Now you can see that we have much less results. Again, we have more than 24 because still something is happening in between. So let's check what. Let's go to time series. And now you can see how our water level in the tank is behaving much more controlled. So we are starting from 3, it reaches up to 5, then it starts dropping until it reaches 1, and then the pump is back on until it's again turned off at this point. Now, if we also add the velocity in this section right after the pump, you can see that during these hours, the pump is closed, and during this hour, the pump is back on. If you need these graphs, you can also draw them to CAD with this icon. So let's click here and let's draw it like this. Or with this icon, you can draw each. Okay, this is all graphs. I don't want this because here I didn't select a tank like this. Now I can draw it like this, so I can see each value on its own graph. Like I said, you can also select multiple values at once. For example, here, let's select this node, this node, this node, and this node. And here, let's select this section, this section, this section, and this section. And now you can analyze it. So these are the pressures in these nodes, and these are the velocities in these sections. You can also here click on this single selection, turn it off, and then you have everything on one single graph. Also, you can go to profile plot graph where you can select some parts of the network. For example, let's go from this node to this node. And this is now basically like a profile. This is a piezometric line, head elevation, but also you can add, let's add maybe the pressures as well. And now you see how the piezometric lines and pressures are behaving during the day. You can also go in time and check how these graphs are changing during the day, or you can switch, for example, let's switch to 4 o'clock, which is our peak flow. Okay, and also you can analyze this with the time dependent labels as well. We can go here to set time function, and now if you click on the arrows, you can see how these temporary labels appear, and you can go through time and check and analyze results also through the labels as well. Let's check this part of the network right after the pump. You can see now the pump is turned off, so the flow is 0. And now when we come to this point, so 7:12, the pump is again turned on and you have the flows. And also if we go to our profile, we can check the dynamic piezometric lines. So check how they are dynamic, they are moving. And for example, when you come to some part of the day that you would like to save and apply, you can apply it. And now these results are applied. So here you have the permanent piezometric lines, you have the permanent label are now applied, and they are now showing our peak flow. And the same is also for our data tables. Let's go to section hydraulics. Let's select, I don't know, maybe this branch. And here you can see that we have our peak flows for our firefighting demand happening at 4 o'clock p.m. Okay, so with this, we conclude the second part of this training. I hope you liked it. I hope you would also like to test it and try it on your own projects.